Good afternoon, everybody, and welcome to the fourth session of the summer term 2024 of Sunoikisis's Digital Classics and Byzantine Studies. The topic of today's session is handwritten text recognition and OCR from papyrus to codex, and it will be presented by our colleagues that you see here on the screen in the order that in which I see them. Maxime Guénette from the University of Montreal, Paraskevi Platanou, who is talking on her behalf and on the behalf of John Pavlopoulos from the Athens University of Economics and Business, whereas Paraskevi is from the National and Kapodistrian University of Athens, as well as Isabelle Marthot-Santaniello, who is from the University of Basel. So, as always, if you're watching this session live, please say hi and tell us where you're watching from. And yeah, having said that, I really don't want to steal any more time from today's session because we have so much to say and so little time. So yeah, without further ado, I would say, Isabelle, yeah, the floor is yours.
Thank you very much. Can you hear me all right? Everything is fine? Okay, good. So many thanks for the invitation. It's a great pleasure for me to be here. I would like to use my time to give you a short glimpse of what is currently at stake with Greek papyrology and why we will rather talk about digital paleography than about HTR, handwriting text recognition. But please, HTR fans, stay. You won't be disappointed. There's a few elements also for you. So please, let's go and have a look. So if my slides want to move. Can you see the second slide? I hope.
Yes.
Okay, good. So very shortly, to start with, what are we talking about when we're talking about papyrological material? Well, we're talking about text produced during the millennium during which Greek was used in Egypt, from Alexander the Great to beyond the Arab conquest. And of course, in such a long span of time, writing practices and scripts have evolved, as you can see with short examples on the slides. But even at a given time, a great variety of texts were circulating. Papyri are traditionally divided into literary text, documentary text, and anything that is in the middle that fits into paraliterary text. Inside each category, we can observe a great diversity of writers, from skilled professionals to beginners, producing rather short text compared to manuscripts. We will be using the word papyrus, but let's keep in mind that 1/3 of the texts are in fact written on ostraca, potsherds, or limestones. And of course, all these objects have various states of preservation. So just to give you a very short example, here you have on the left and up a contract, and on the lower down a carefully calligraphic text that those that will pick the exercise may encounter again. So that was for the raw material. And if you're familiar with HTR, you will have already noticed that the description I just gave you is not the optimum one to hope for decent HTR results. Let's shortly now turn to the current state of research. And first, we'll have to make a distinction between published and unpublished texts. We don't know exactly how many unpublished papyri are in the collections. It is not rare that large collections have several thousand of unpublished texts. For Oxyrhynchus' collection in Oxford, for instance, it is said that there's 500,000. Some still require restoration, others are already digitized and catalogued, but the general policy is to keep the unpublished papyri for study, and here I mean traditional papyrological study, a little bit like archaeologists have not rushed to skim through Pompeii, but have led careful excavation and left part not yet excavated. It is the same philosophy operating in papyrology. Papyrologists would rather have only careful editions of fewer texts than approximate transcript of every fragment, lacking proper study. That's the main reason why there is no demand for HTR from collections and papyrologists for now. With my colleagues from Bern, Tobias Rodel, we gave a little try on HTR in 2020 to get an idea of the time cost, the possible pipeline, and the various problems to be expected. Of course, since 2020, we would have much better language models for ancient Greek, and I'm sure the following presentation will tell us more about that. So we wrote a short article and we stopped quite early because we were not really interested in HTR, but anyone interested should not hesitate to contact me and I will share the preprint. Unless for exceptional cases, unpublished papyri are not treated automatically. And when I talk about exceptions, I'm also, of course, thinking about Herculaneum papyri. And you may have heard about the Vesuvius challenge that was launched last year, and that does not stop announcing outbreaks. And also another project that has recently announced that they managed to read new passages of carbonized worlds and learn more about the end of Plato's life. It was in the news recently. So what I would like to talk about now is digital papyrology focused on published text, meaning available transcriptions. We have a little over 80,000 texts that received already a proper edition and a catalog in Trismegistos. So for those who will be taking the exercise, you will have to look a little bit what are the information that are provided in this platform that is called Trismegistos, what kind of metadata and what gates it consists to other resources. I will leave it for now. So thanks to the efforts, a general effort in the discipline that started in the 1970s, 60,000 texts have encoded transcription on papyri.info. It means it's almost up to date on documentary text, but still missing on literary and paraliterary text. And that's where a project could maybe efficiently use OCR on printed edition to speed up the process. I say maybe because it would still be challenging due to the short size of the text and the various edition modus operandi. So anyone interested about the textual content of documentary papyri should have a look at the possibilities offered by papyri.info. Now, I would like to talk about the digitization, meaning the production of a digital image of a papyrus. It started 20 years ago, roughly, but of course, this also depends a lot on the collections. We have a series of online catalogs with various qualities, various metadata, and various copyrights. Usually, it is quite easy to look for an image of a given papyrus, but we don't have something that would be a virtual library gathering images across collections. I don't have time to go further into the details of digital papyrology in general, but anyone interested in the subject should turn to the excellent survey by Nicola Reggiani from 2017. So rather than, so you would have guessed that rather than HTR to automatically transcribe unpublished papyri, there is a strong interest in text-image alignment on published papyri. Currently, Rodney Ast in Heidelberg and Holger Essler in Würzburg are working on this topic using the platform called eScriptorium, and we hope to hear from them interesting results soon. There are a few initiatives that collect papyri according to precise criteria, thus constituting what would be the closest to a dataset of images. First, we have PapPal that gathers several thousands of precisely dated text. Then we have the collaborative database of datable Greek bookhands, which, as you have heard, is dealing with datable bookhands, so literary scripts that have reasons to be dated to a certain period. And I mentioned a last example of the BPAB that gathers all the images of the papyri from the Byzantine period found in a village named Aphrodite. So that's a little bit the situation when I started to work on digital paleography. As a papyrus editor, I was frustrated to think that some fragments of the papyri I was working on would be in collection, and I dreamt of searching through the images like we were able to search through the text. So in 2018, thanks to a grant from the Swiss National Science Foundation, I started in Basel a project entitled Describes, Reuniting Fragments, Identifying Scribes, and Characterizing Script, the Digital Paleography of Greek and Coptic Papyrology. I won't talk about the reunion of fragments today. I will quickly say a word on writer identification, and then I will focus on the question of script characterization. So, to identify writers, it is not an easy task because we don't have the data ready. We don't have in a single place a list of texts written by known writers. And so I had to start the data set from zero, and I chose the largest archive of the Byzantine period, the Dioscorus archive, which, as you have seen, had already all the images gathered in one place. So here is a data set that I could compile, collecting 120 samples of 23 notaries of this village, and I am absolutely sure that the notaries have written the body of the text. And you can see how diverse are these images, as we said, state of preservation, but also digitization. So to give you, in short, the results of the research that has been going on the last years, the writer identification methods that come from forensics work pretty well on papyri if, with a big if they are enough well-preserved samples, and it works especially to discriminate one writer to another. What I mean is that the network could recognize a notary that was attested by only one document, but a very large document, and his name is Dios. But the same network had problems to recognize the handwriting of a notary that was attested by several writings spread across a period of 30 years. So now what is really at stake is to be able to find a hand that may change across time and across documents. So that's where we are on the topic of writer identification. So if you're interested, there's a lot of material on the website of the project, describe.org. There's a section that is called case study, and you have a series of data sets and of articles that are on the subject. So now there's still some minutes to talk about the script characterization. So for writer identification, we need ground truth. So we need first text we are sure of the writer. And this is challenging, especially for literary text, because we're not at a period where we have colophons. So the people that were copying the manuscript at this period were not saying their name, the date of the copy, the place of the copy. So what is left is only the appearance of the handwriting, and very often we don't have archaeological context. So what I mean by script characterization is extracting useful information from the shape of the handwriting to gather scripts and styles that share similarities. And then the reasons for these similarities need to be made explicit, and this is part of interpretation. So I used first a data set made out of Iliad papyri from Homer. So altogether, we have more than 1,500 papyri bearing the text of the Iliad spread across the millennium. But the datings are discussed and the typology. There's no consensus on the typology except a few specific typical scripts. The description and the belonging of a text to a certain style is discussed among specialists. So what we did is to use a platform called READ, the Research Environment for Ancient Documents. And this platform allows to tag the image with the transcription. So you see here a papyrus with bounding boxes that were manually drawn around the letters. And once the work of annotation is done, you can see all the alpha of the text and of the image in a glimpse. You can see also the alphabet. You can display this alpha and you can assign them tags. And that's what we did with tags pertaining to the state of preservation. We wanted to we tagged everything, but we wanted to be able to select only the alpha that are the best preserved. And you see that's the ones that are called BT1. What we did is, because this read interface is quite heavy to take at hand, is to do a viewer that is easy for sharing the results and the annotation. And that's something the people that will do the exercise will have to explore a little bit. And this viewer also allows to see all the specimens of the letter. And at this point, it makes progress compared to traditional paleography, which often had to choose one typical example of an epsilon. Here, you can keep all the well-preserved epsilon and not have to choose which one is the typical one. The other important feature of READ was the possibility to export all these images into cliplets or small images. And that's what we use with artificial intelligence in a paper that was suggested for reading. And that allowed to measure similarity scores among papyri. So we focused on 3 letters, alpha, epsilon, and mu, and on 72 literary papyri. And by teaching the network what is similar, what is dissimilar, defining similar by 2 letters that come from the same papyrus, we were able to have similarity scores. And so, thanks to these similarity scores, we could look at different thresholds of similarity and see patterns that correspond to traditional stylistic descriptions. For instance, one of the canonical handwritings is the biblical majuscule, and the biblical majuscule shared common similarities in our results and were grouped together. And what is also interesting is that is the granularity of the results. So you can look at the papyri that have the best scores combining the 3 letters, but you can also have a look individually to the most similar mu, the most similar alpha, and epsilon. And this is what the people that will have to do the exercise will have to look at is what we can interpret in the similarity that is found into this papyri. So I go fast from this because that will be the core of the exercise. So you see all the things that we can do once we have the images annotated at the character level. But of course, it was done manually and it was very time consuming. So last summer, we did a competition to automatize the detection and recognition of Greek letters and papyri. And now we are experimenting this semi-automatic annotation, and we hope for good results of around 80% that would really allow to speed up the process of tagging. And since last June, Describes project was finished and a new project started called EGRAPSA that wants to embrace the evolution of handwritings at a large scale. So the idea is to have a comprehensive history of the evolution of Greek handwritings in their social and cultural context. What I mean is to look at the text not only on the chronological perspective, but also according to the social cultural context of the writers. And starting with solid landmarks being able to establish that a given text is most similar to this and this text written by this kind of person in this kind of period. So to conclude, what was important in my experience of digital paleography is the importance to carefully prepare the data sets that are the most solid and the best adapted to your research question. Because I started with the beginning of AI, and I had the feeling that some colleagues were really trying, testing, and say, let's try and we'll see what we'll get. Well, that is very a dangerous way. What is important is that we find the way to work together with computer scientists. And there's the question of different speeds of publication, for instance, publishing the results, but also the in-depth analysis. And that's what the exercise will show, that once we have the results of AI, how much paleographic and papyrologic work is still to do to make some meanings out of that. But I'm really convinced that this is really a benefit both from papyrology and computer science, and not one working for the other, but really improvement in both sides. And to manage this great collaboration, it's important to create a community. And so there's a web mailing list that I warmly invite you to subscribe if you're interested in digital paleography, whatever the script or the writing material. And with this, I see that I'm just over 20 minutes. And so I thank you for your attention.
Thank you, dear Isabelle. This was brilliant. I see that we have some comments, but if it would be better if we address them at the end. So I will keep this in mind and I will show it later. So now we have Paraskevi and John, but if I understood correctly, Paraskevi will talk on behalf of both of them. So I will share your screen, Paraskevi. And yeah, if you want to share your slides, we're there. So perfect.
Can you see my slides?
Yes.
For slide mode, right?
Perfect.
All right, thanks. To begin, I want to thank the organizers also from our side for the kind invitation to the session, and also on behalf of John. I will be presenting my and John's latest work on HTR. At first, I will present the challenges and potential mitigation strategies regarding HTR, handwritten text recognition, for old Greek manuscripts, focusing on manuscripts from the 10th to the 16th century. The project presented involves transcription of images from the Oxford University Bodleian Library Greek manuscripts collections and creation of a new dataset for handwritten paleographic Greek text recognition, data classification by century, and experimentation using the Transcribus artificial intelligence platform. Results saw varying error rates across centuries, with higher error rates observed in later centuries. Error analysis reveals challenges such as missing spaces between words and character merging. We will then explore the challenges of post-correcting errors in handwritten text recognition, particularly in Byzantine Greek texts. When utilizing state-of-the-art language models pre-trained in both modern and Byzantine Greek, we observe remarkable average precision scores, further enhanced by incorporating elements of ancient Greek language. A century-based
Paraskevi, I think your slides are not moving. Sorry to interrupt. We're still on the first.
Fine. Thanks. I'm not moving the slides. It's fine.
Okay. Oh, good. Okay, sorry.
So this century-based analysis will reveal the advantages of classifiers pre-trained in ancient Greek, particularly evident in historical textual contexts. By integrating these classifiers prior to neural post-correction mechanisms, we showcase then a substantial reduction in post-correction errors with HTR outputs. Now I move the slide. Can you see it?
Yes, thank
Fantastic. Now, before going to the HTR various experiments we will be seeing today, it will be useful to say a few words about the language first. Here I am quoting Martin Hiddebeck in the newly published Oxford Handbook of Byzantine Literature, edited by Stratis Papaioannou. Byzantine Greek evolved from classical Greek education. This education, based on Hellenistic and Roman textbooks and the study of classical texts, shaped the written forms of medieval Greek. Byzantine discursive culture resulted from the interplay between traditional written forms and spoken Greek. Prose for non-literary works, termed literary kine, blended spoken language with ancient Greek morphology. Recent studies show that even higher register Greek reflects contemporary spoken language. Modern studies categorize Byzantine language into various terms such as Attic, classical, or vernacular. However, the Byzantine understanding of these terms often differs from modern interpretations. The language of Byzantine texts was shaped by factors like education, audience, genre, and literary trends. Classicizing trends influenced literary language, reflecting cultural and political shifts. Classicizing authors were inspired by their literary heritage but not bound by it. Instead, Byzantines creatively incorporated traditional elements into their compositions. In morphology, Byzantine writers, influenced by hyperclassicizing tendencies, expanded existing patterns into areas not well attested in ancient Greek. Forms like pluperfects, often lagging augment, and sigmatic aorist steps were used even in texts with a classical style. Until the 13th century, vernacular morphology was largely excluded from literary texts, but occasional appearances were found, primarily in subliterary works. Only from the 13th century onward did a literary vernacular emerge based on contemporary spoken Greek morphology. Byzantine texts featured innovative syntactic constructions like circumstantial infinitives and verbal periphrases expressing anteriority. While influenced by older texts, Byzantine authors had a broad range of linguistic possibilities at their disposal, resulting in alternative forms and syntactic constructions. Now, Byzantine vocabulary served as a bridge between high and low registers of Greek. Despite their reverence for ancient Greek, Byzantines occasionally reinterpreted words to fit contemporary contexts, such as assigning new meanings to morphological categories. This demonstrates their adaptability in reshaping linguistic heritage to suit their own cultural and linguistic milieu. Now, we'll get a glimpse of the field of Greek paleography, which involves analyzing various styles of writing used in Greek manuscripts. The scripts, often referred to as hands, evolved over time and varied depending on factors such as geographical location, time period, and the scribe's individual preferences and training. Here we can see some examples from various centuries. On top left, we can see a 16th century informal minuscule slightly slanting to the right. And then on your right, you can see a 14th century mixed minuscule script slanting slightly to the right again in brown and black ink with moderate variation in letter size. We notice that syllabic abbreviations and superscript word endings appear throughout the line, breathings are out, and mute iota is absent or subscript. There is frequent decorative use of the double dot and accentuations of all nomina sacra. Accents are sometimes joined to letters, breathings, abbreviations, and nomina sacra strokes. Horizontal strokes appear over proper names. Then on bottom left, we can see a 12th century upright mixed minuscule script, which is similar to parascript in brown ink with little variation in letter size, I can say. The use of the double dot is functional only here. Punctuation marks include the lower, middle, and upper points, lower comma, question mark, and full stop. Then on your bottom right, we see an 11th century mixed minuscule script, again slanting slightly to the right. There is again some modest, I can say, variation in letter size. Abbreviations take an angular form, breathings are both angular around, and mute iota is adscript. There is also music notation in this manuscript. The text has been provided with ekphonetic notation in red ink. And then there is also this 10th century manuscript with a mixed minuscule boulette script, slanting slightly to the left in brown ink, with variation again in letter size. Syllabic abbreviations are not used. Majuscule letter forms in use include gamma, delta, epsilon, kappa, sigma. We see various letters. And now, that said, I will present to you the first project, handwritten paleographic Greek text recognition by century. In this project, our dataset consists of 77 images from the Oxford University Bodleian Library Greek collection of manuscripts. The images of this dataset that are used are grouped into 7 categories according to the century to which the manuscript dates, that is, from the 10th century to the 16th century. In total, 7 centuries and so 7 categories. What are the characteristics of this dataset? Both the Greek minuscule script and the cursive style of the minuscule script are represented. There is often no empty space between the characters. There are characters of various sizes, characters with different kerning and baseline offset, ligatures, that is character unions, both uppercase and lowercase letters. And finally, there is a tendency towards placing breathings, accents, and other marks, not above the associated letter, but somewhere further in the text. In order to create our model, we use Transcribus, which is designed to accommodate artificial intelligence-powered text recognition and transcription of historical documents. We first start with layout and then transcribe. But How do we transcribe effectively? And how do we manage the layout effectively again? In figure 1, we see the transcription process in Transcribus, and in figure 2, the layout recognition. Students who will choose the exercise will have the opportunity to experiment a bit and explore further possibilities by Transcribus. The layout analysis, as you can see in figure 2, can be extremely challenging. And figure 2, I feel it serves as a good example of challenges the transcriber may face. What can we do with the text in the margins, and what can be considered as margin when transcribing? How can we include text through the lines in the layout analysis? And what is its place in the transcription? These are only a few questions we need to ask ourselves when starting the HTR process. It is usually the research goal that will enable us to understand how the HTR should work for us. The next step is training our model. We selected 63 out of the 77 images for training, and we used 7 images for validation and 7 images for testing. The selection was stratified across centuries so that 1 image per century was used for validation and another one for testing, while 9 images per century were used for training. So we used the training and validation data to train Transcribus, and in the third step, we reported its accuracy on the 7 test images. Now, plotting the character error rate against the individual centuries the text comes from, as you can see in this figure on your left, we observed an imbalance in character error rate across centuries. Although the model performs well in the first 4th century image groups, poor character recognition performance characterizes the century image groups after the 13th one. The figure on your right presents the word error rate scores, which are higher than the character error-based scores. A similar imbalance is shown with word error rate being much higher for images of the last 3 centuries, from the 14th to the 16th one, but with the highest error rate now corresponding to the 16th century. And now, in the 4th step, we proceed with the error analysis. The dataset organization by century enabled us to find that character error rate varies across the centuries of interest. Words are not easy for the model to recognize because of the often missing spaces between them. The model cannot really detect spaces where there is no clear character separation. And although there are reasons which can account for false word recognition, such as unexpected empty space between characters of the same word, or size inconsistency between characters of the same word, then the cause of misinterpretation of individual characters is not that obvious. However, error analysis combined with a better look at the characters reveals that a considerable number of characters in the case of the 14th, 15th, and 16th century datagraphs present at least one challenge. In other words, characters may seem to be the result of a particular procedure, which is usually merging, grouping, or symbolization in these cases. there is a tendency towards cursive writing style in the particular pages, which leads to character union. The scribe did not lift up the hand at the point at which the next character was to be written, and hence the result. Another way of writing characters, which is quite interesting, is matching characters with symbols. In this case, we can see that lines and character lines stand for specific character combinations, and they usually appear at the end of the word of the line. So what we wish to show here is the fact that when the model is to read such complicated characters, it is very possible that it will make false predictions leading to high character error rate. Here you can see such possible cases of false prediction. For example, you have on your top right of the screen Selenon, where you have an unexpected space that might be falsely predicted by the model as two words, whereas it is only one word. And then you have this impressive combination of U and No in one letter form, as well as the case of sigma and ta. You have the example of st or stomati. And then you have again epsilon and iota, or epsilon and upsilon. These are all very, very interesting combinations. I will also show to you now some examples from the character error rates. So in this century, that is the 16th century, we can see that we have the data group with the highest average character error rate. What seems to be challenging in this data group is the fact that there is a variety of punctuation marks which are sometimes read by the model as letters because of their shape. An illustrative example of this case is the word plus, which is read by the model as plowo. This is due to a comma following the word plus, which is very similar to the last letter of the word. There were also many cases of ligatures in which the model fails to recognize both letters, especially the one written on the top of the ligature, such as the letter taf in the combination taf and ro, as one can see in the following instance. O patris read as O Paris. The data from the 14th century show the second highest character error rate on average. This is partly because of a great number of ligatures appearing in this data group. A common ligature among this group is the one which represents the group of the letters epsilon and rho. In this ligature, it happens that the letter epsilon is written above the letter rho. The way the model interprets this structure can be seen in the presented case, where fair consists of one letter phi and one ligature epsilon rho, is read by the model mistakenly. The same instance shows clearly that there is a tendency towards adding characters because of different drawing representations of characters found in this data group. In the same example, we can see that the word io is read by the model as iso. This is because in this instance, the letter omega has the shape of a horizontal 8. The same letter has the usual shape in other cases in the text of the century, which was quite confusing for the model and led to the model to decide that it should be a combination of both sigma and omega. Well, great. And now we got this erroneous output. If going back to the previous step seems not promising in the sense that no alternative can provide efficient recognition, Then, the other alternative is going forth. But how? Perhaps inferred already from the previous slides, but we can make it more explicit. Applying the HTR on old manuscript is not easy, and it is why we observe diversity in character error rate, with lines perfectly recognized to lines with scrambled output. But correcting the erroneous output is not an easy process. While avoiding correcting the HTR output, this delays preservation and hinders further recognitions. A reasonable hypothesis, then, is that the detection of an erroneous recognition is easier when the recognition output is scrambled compared to an output with a single incorrect character. That is, automatically detecting whether the HTR output is correct or not is an easier task when many errors are included. Or to give an example in the right context, classifying recognized text as erroneous or not is easier for the human eye in the right case compared to that on the left. We hypothesize that this applies also to models. Detecting erroneously recognized text can improve automatic error correction. Consider a flawless text, for example. Then encoder-decoder based post-correctors are faced with a high possibility to introduce, instead of mitigate, errors that would be absent if post-correction hadn't been applied. I would like to know that this study, the new project I'm talking about, focuses on the Greek language only after the first millennium, but this doesn't make it out of scope. We have already saw that as time progressed, elements of contemporary spoken Greek gradually became integrated into the Atticized Greek, and as a result of this study saw, pre-training on modern and ancient Greek is beneficial for text classifiers detecting incorrect recognition output. The descriptions and the HTR output for this project come from a recent challenge called HTR, which recorded the automated correction of HTR errors in Byzantine Greek. Selected images of handwritten text in respective manuscripts were transcribed. An investigation of the character error rate of this recognition model reveals the diversity of errors discussed earlier, from very few to many per line, which are not uniformly distributed across centuries. So to set up a classification experiment, human transcribed lines were treated as the negative class shown in green, and the respective system recognized lines were treated as the positive class in red. Classifiers can now be trained to detect whether any text, as the one coming from this image, is erroneous or not. Here it was found correct and was classified as green. A random baseline draws the lowest performance, which was outperformed by conventional machine learning methods on top of 10 frequency inverse token frequency representations and character engrams. The best was a multi-layer perception. Deep learning methods comprise a recurrent neural network that perform comparable to the MLP, but the deeper and pre-trained BERT models were better as expected. Further pre-trained in ancient Greek is the best in all metrics. And here we come back to the Byzantine Greek discussion we had earlier. Specifically, the BERT model that was pre-trained in modern Greek and then further pre-trained in ancient Greek was the best one, perhaps because this language combines language elements found in both ancient and modern Greek. We grouped the test lines based on the century of the manuscript they came from, and we evaluated the two transformers, the pre-trained in modern shown in light blue, and the one that was further pre-trained in ancient Greek that is shown in light red. And we see that the classification performance depends on the chronology of the manuscript, with older manuscripts being better handled by a model that has been further pre-trained on ancient Greek. The red one is better on the 10th and 11th century. Models perform equally high on the 12th and after the 13th century. On the 13th century, the performance of both models drops, but considerably more for the blue that is only pre-trained in modern gray. The 14th, 15th, and 16th century were more challenging in HTR, as was already shown in the prior work, which could explain the better performance of the classifiers. On the other hand, lines from recent manuscripts pose an easier classification challenge. But these 3 centuries are more challenging in HTR, which can explain the better performance of the classifiers. That is, the more errors in the recognized output, the easier it will become for a classifier to distinguish an erroneous line. Although class-balanced, our dataset remains imbalanced at the character error rate level, meaning that there is a diversity of errors for the different lines. So by creating character error zones from low to high, we can see the performance of the models. We can see that high character error rate lines appear to set an easy classification task to both models. Performance increases as the error increases. This is reasonable, considering that lines with a high character error rate comprise many errors and are hard to parse, even by humans. This characteristic, however, makes them easier to distinguish from flawless lines, which comprise no errors, from their recognition. Low character error lines, on the other hand, suggest a different picture. Low character error rate means small differences between the two types, flawless and flawed, which makes the classification task more difficult. In this zone, further pre-training on ancient Greek had a bigger impact compared to zones with a higher error rate. So the classification brought us some interesting findings, which wouldn't have been easy to unlock outside an interdisciplinary team, and I would like to stress that. The same stands for explainability. We undertook an error analysis task where we asked the experts to manually evaluate lines and compared with model outcome. For this line, the model mistakenly classified it as flawed. Why? Judging from the network's attention, the rare word philakoluthos has a double accent, right? And it is the subword with the second accent that attracts most of the attention of the model. So the model is probably not exposed to words with double accent. Another interesting example is the word Ismailiti. It was considered as a misspelled outcome by the classifier, but not by the experts. In this case, it was the ending of the word that attracted attention, but the network focused more on the article that precedes the word, ton, rather than the word itself. The article is in plural form, ton, not matching a word in singular. Apparently, Ismailiti is not a misspelling, but part of the word Ismailitikon that was corrupted. And that said, I will finish the presentation here. And I will give the floor to Maxime.
Thank you, Paraskevi. This was brilliant, and I already see we have some questions and comments for you too, but we're going to get there after Maxime's presentation, whom I invite on the stage. There you go. The floor is yours, Maxime.
Thank you. Thank you. Just gonna switch. Perfect. Can you say changing? Oh, it's not. Sorry, Martina. It's not actually the good one. Oh, okay. So now it's changing.
Yeah. If you try and change once more.
Perfect. And then
we don't see any changes though.
Yeah, I'm just gonna do that and do that. Okay, perfect. So now you can see my slide changing, right?
Not yet. Try once more. I mean, we still see the first slide.
Okay, perfect. Sorry about that, guys. I'm just gonna change it again then. I'm gonna stop the why is it not changing?
We had it all planned out, but there was a drop in the connection, so don't be don't be scared.
Okay, so now you should see something.
Wait, try and change your slides.
Is it changing?
Yes, but we see your notes.
Oh, we don't want that.
Yeah, but now it's all right. There you go.
Perfect.
Yeah.
Perfect. Thank you. Sorry for the slight delay. So we're going to talk today about decoding ancient Greek, particularly with the use case in the case study of the Palatine Ontology. So this research is part of my involvement within the collaborative digital edition of the Greek Ontology project, which began 10 years ago now at the Université de Montréal in Canada. The Greek Ontology is a collection of poems, mostly epigrams that span through the classical and Byzantine periods of Greek literature. During an internship in digital publishing at the Université de Montréal in the summer of 2023, me and the team became interested in handwriting recognition of ancient languages, more particularly ancient Greek, and how can this technology could be applied to the main manuscript of our project, so the Greek Ontology. The main witness of the Greek Ontology is the Codex Palatinus Graecus 23, otherwise known as the Palatine Ontology, which is kept in Heidelberg in Germany. It is important to distinguish the Greek Ontology, which is the collection of epigrams, and the Palatine Ontology, which is the manuscripts itself. The Palatine Ontology is a 10th century Byzantine manuscript, which, according to the Belles Lettres critical edition, contains the hand of 4 scribes or copyists, so A, B, B2, and J, and also 2 lematists, C and L. It has been digitized and is now available on the website of the Heidelberg Library. It should be noted, however, that during one of the many journeys of the Palatine Ontology, the manuscript was torn in 2 on page 614, the second half of which is also digitized on the Bibliothèque Nationale de France website as the Parisianus Supplementum Graecum 384. So the digitization of ancient manuscripts by the GLAM, so the galleries, libraries, archives, and museum, is extremely useful for anyone wishing to consult them. Most of the time, these precious manuscripts are kept in archives with restricted access, and only a few people have physical access to them. However, there's still a problem. Although we have digital access to these manuscripts and other documents, all we really have are visual supports in image formats such as PDF, JPEG, and others. So the text of these documents still eludes us. Without this access to the text and its materiality, the potential of these digital surrogates is not fully exploited. For example, it is impossible to perform a simple word search or even so more advanced text analysis. With approximately 2.5% of Greek literature having come down to us, it is then vital to have access to these manuscripts that have given us these precious texts of antiquity. We then propose to use HTR, which is short for handwritten text recognition, to access the text of the Palatine Anthology and more generally the texts of ancient Greek manuscripts. HDR is a type of technology that can be used to read and writing in images of any documents. Let's say you've written an essay by hand, and now you want to have this essay in a digital text form on your computer. With the right HDR software, you can take a photo of this copy of your essay, run it through the HDR software of your choice, and then get the same copy as a digital text file that can be downloaded and shared as needed. This is the basic principle of handwriting text recognition. A more familiar maybe and similar process would be OCR, which is the optical character recognition for printed text. Although HTR has been popular technology for several years now, its application to ancient Greek is relatively recent. And as a result, there's very little ground truth available for ancient Greek. In short, ground truth is the set of accurate, verified data used to train machine learning models for HTR. It is simply just the transcription of the text of an image. For example, as you can see on your screen, the transcription of the text would be Iulianu. The causes of lack, or rather absence, of ground truth for ancient Greek are manifold. For most non-Latin scripts, such as Arabic or ancient Greek, there's a mismatch between these writing systems and scripts and with other languages, such as English or French. One obvious reason for this is the amount of primary data available for each writing systems. There are infinitely more documents in English, or at least using Latin characters, than in ancient Greek. This difference influences the over-specialization of handwriting recognition tools towards the Latin alphabet. The number of specialists would be also an important factor for the lack of ground truth, because the fewer specialists there are for a given language, while the fewer documents will be transcribed and annotated. But as we can see today, well, there's a growing number of experts in ancient Greek who are interested now in HTR. Finally, the scarcity of ground truth for ancient Greek also results from the absence or obsolescence of recognition models produced by research. So with that in mind, we then came up with an HTR pipeline that can be divided into 5 distinct steps or stages. The first one is the digitization of our manuscripts or documents. The second step is to acquire images of the manuscript. The third one is to import these images into our chosen HTR platform, Scriptorium, for text segmentation and transcription. The fourth step is to train the recognition models using Kraken software. And the fifth and final step is to deposit our data using HTR United and Zenodo. Let's take a closer look at the different steps of our pipeline. The first one, the digitization of the manuscript of the Palatine Anthology, was carried out by the Heidelberg Library in 2009, and it was made available on their website. This brings us to the second step, images acquisition. 3 download options were made available on Heidelberg Library website. You can download it on JPEG format, PDF format, or by IIIF import. IIIF import is for International Image Interoperability Framework. We chose the IIIF protocol because it guarantees the quality of the image transfers, and also because it can import the manuscript submitted data on your HTR platform. From the complete import of the Palatine Anthology, we then selected 2 samples containing mainly the hand of scribe A and a few comments by lemmatist C. The third step of our pipeline is the segmentation and transcription of our images directly on a scriptorium. The scriptorium was developed by the Scripta team at the Université Paris Sciences et Lettres and is an open source platform offering a graphical interface that facilitates the use of Kraken. Kraken is also open source and is an HTR software developed by Benjamin Kiesling in 2015 and was initially designed to provide better support for recognizing non-Latin scripts, particularly Arabic. In addition to Kraken's HTR features, the scriptorium offers a number of advantages for our project. Local or server installation, import of images using the IIIF protocols and transcriptions in XML format, export of transcription in XML, DEI, or even plain text, and finally the production of segmentation and HTR models. We used the scriptorium on the Crema server. Crema is the Consortium pour la reconnaissance d'écriture manuscrite des matériaux anciens. It's a group of HTR specialists based in Paris that can provide an access to their server. And the access of the server can allow us to work collaboratively and simultaneously. Once our images have been imported into a scriptorium, we can then proceed with layout analysis and zone detection. We use the Segmento ontology to standardize the vocabulary used to describe our layout. The Palatine ontology is fairly simple. The body of the epigrams is the center of the page in purple here, while the scholia, the comments, are in the margin in pink here. 2 segmental zones are used, main zone for the epigrams and margin zone for the scholia. As for our lines, we have used the default line category to describe the vast majority of them, and interlinear line as for, you may guess, interlinear lines. A default segmentation model is available on its scriptorium, which can be used to adapt it to your zone and line types. After segmentation, we are finally ready for transcription. The transcription is usually the longest step of any HTR pipeline. We had to manually assign transcription to each one of the lines in our samples. For total of 70 pages, we actually put maybe 125 hours, or on average, there. So to do the transcriptions, we used Hugo Stadtmuller, critical edition of the Palatine Anthology, dating from the late 19th, early 20th centuries, and which is available on the Internet Archive website. For any transcription in HTR projects, guidelines should be followed in order to standardize our data. We therefore decided to standardize all sigmas into a single form, partly to reflect the handwriting of our scribe. We also developed the abbreviation most commonly found in scholia, Note, for example, on the second line of the image, the abbreviation for the omicron and upsilon at the last word, kepuru. For important symbols, for example, the tilde at the end of the scholia in the image, we have transcribed them with visually closed Unicode symbol. A virtual keyboard can be created on a scriptorium to help us add these symbols. Finally, we also have standardized all punctuation with the interpoint and the colon to make it easier for our models to recognize them. Once our transcription is complete, we can now move on to the fourth stage of our pipeline, training models with our first sample of 50 pages. This training produces two types of model, a segmenter and a recognizer. Our segmentation model is fine-tuned on the default scriptorium model. Trained with our first sample, it is able to detect text areas and lines in our manuscripts and then classify them according to the segmental ontology. Despite the fact that there is no effective metric for calculating the effectiveness of our segmenter, we can say that it gives visually conclusive results. The recognizer is for recognizing handwritten text. It's indeed the HTR models itself. We have then two options to train our models directly on a scriptorium, which uses Kraken, or to use Kraken directly on the command line. Since it was no longer possible to train models on the Crema server for technical reasons during our experimentation on August 2023, we switched directly to Kraken on the command line, which also allows us to adapt the training comments more effectively. Then with Kraken, we trained 3 different models in NFC and NFD. It's worth saying a few words about the Unicode standard from which our NFC and NFD models are derived. Unicode is essentially a computer standard for representing and encoding text characters of different languages, symbols, or special characters. Depending on the chosen Unicode encoding, 2 visually identical characters can be understood completely differently by a computer. Let's take the example of omega with a rough breathing and a circumflex accent. With the normalization form canonical composition, NFC, this character is represented by a single Unicode character. So the omega and the diacritical marks have been composed by the computer. With normalization form canonical decomposition, NFD, the computer breaks down our character in 3 different Unicode characters. NFD is particularly useful for a writing system with a large combination of diacritics, such as ancient Greek. So our preliminary results are very encouraging. We trained a first model in NFC from scratch, which is without a base model that could be improved using our data. This model gets an accuracy score of 87.36%, meaning it got the letter or symbol wrong 12.64% of the time. We also trained 2 other models in NFD, the first one from scratch with an accuracy score of 89.96% and another one fine-tuned, so based on the generic Crema medieval model with an accuracy of 89.16%. Crema medieval is a model trained on a large number of Latin and Old French manuscripts and provides a generic model for medieval manuscripts. To improve our 2 types of models, we decided to run a second sample of 20 additional pages, bringing our total of pages to 70. The logic behind this decision is fairly simple. With more data, our models will be more efficient and accurate. We therefore improved our segmentation model, which is now more accurate than it was before, although we cannot really calculate the difference in performance, sadly. For text recognition model, we proceeded in the same way as the first training session. So we managed to gain actually a few more points in terms of accuracy. The NFC from scratch model achieved an accuracy score of 91%, and the NFD from scratch 90.85, and finally the fine-tuned NFD from Crema Medieval 91.5%. Finally, our fifth step in our pipeline is something that is often overlooked by the scientific community. It's not enough to produce data or HTR models. We also have to publish them online and make them fair. So, acronym for findable, accessible, interoperable, and reusable. To do this, we use two complementary platforms, HTR United to catalog and create metadata for a transcription, and Zenodo to catalog our various models and create a DOI. So in conclusion, the results of our experiments of the Palatine ontology are very conclusive and have allowed us to make a number of observations. We're able to achieve a rate of accuracy at 91%, and so, which is considered acceptable for text analysis. At the very least, it will be much quicker to correct errors using our models than when you're transcribing something, than transcribe everything by hand. We also know that despite the lack of a generic model in ancient Greek, we have achieved satisfactory initial results with around 50 pages. However, as we saw when training our second sample, a 70-page sample performs better than a 50-page one. Finally, we see that it's possible and even effective to fine-tune generic models such as the Crema Medieval for scripts such as ancient Greek that does not have at the time a public state-of-the-art HTR model. Although our results are encouraging, we must bear in mind that there are some limitations into our experiments. First, our segmentation model is only trained to recognize the rather simple layout of our manuscripts and will not give out satisfactory results for other documents with complex layouts. Secondly, our transcription models were trained almost exclusively on the end of scribe A, an old round minuscule from the 10th century. It is therefore less effective at recognizing the handwriting of any other copyist, even within our own manuscripts. So, thank you. And if you want to access our data and models, you can go on this website, which is a GitLab website. Thank you.
Thank you, Maxime. This is amazing. And also thank you, everyone. Thank you, Isabelle. Thank you, Paraskevi. Thank you, John. It has been great. So I would say we still have some time for questions, which is surprising. So I would say let's address some of the comments that we already had. So I think that the first one by our colleague, Lev from Innsbruck, hi, Lev, was for Isabelle. So he was wondering if, would you like to address this?
Yes, so Lev is absolutely right to point out that we have only used 3 letters, alpha, epsilon, and mu, to measure the similarities. And we can indeed hope that adding features, so adding more letters, will improve the similarity measurements. The limit is the unbalanced frequency of letters. So we have 13 alpha for 1 psi or something like that in the Greek language. So that's what also we were limited to. And so we run a little experiment on the competition data set. On the competition data set, we had 150 texts that were labeled at the character level. And if we wanted the 8 most frequent letters attested 2 times in a good quality, we had to give up more than half the text. So we dropped to around 60 texts. So this is really a challenge because we, of course, as paleographer, we would like to compare everything, but the data is here and it is damaged and we have to do also with that. But that's definitely something we would like to go in the future, and improving the automatic detection and recognition will provide more data.
Thank you, Isabelle. And I think that the next two comments by Lev there for Paraskevi and John. So I will put them on the screen. This is the first one. No, wait, I'll stick to the first one. Yeah. So Lev was wondering if there is any open access code that shows the implementation of Greek birth or ancient Greek birth for, and so on and so forth. Yeah.
So I will go by asking both of them. In our study, we actually fine-tuned two birth models pre-trained in Greek. The first one that was pre-trained in modern Greek was the one by Koutsikakis, Chalkidis, Malakasiotis, and Androchopoulos' work in 2020, and the other one we extended. I mean, the other one was extended the first one by being further pre-trained in ancient Greek. And this was another work in 2021 by Singh and others. So we actually did the fine-tuning. This worked for us in this case. And yeah, you can also refer to the deep learning benchmarks we used in our paper. And this paper is called Detecting Erroneous Handwritten Byzantine Text Recognition.
And I think it's also required readings for this session. So it's also very accessible. Thank you, Paraskevi, and thank you, Lev, for your very nice comments. So I shall ask...
Martina, sorry for interrupting. I see that there is a comment by John in the private chat, so maybe I can...
Sorry.
No, because he can't put it in the public chat, so I'm pasting a comment here. Perfect. By John. So just in case, as you can see, so this is the comment that John was putting in the private chat. So this is for everyone, and this is also in our YouTube chat, so for people listening to us.
Perfect. Thank you, Monica. I didn't have an overview on the private chat, sorry. But I think we have another question from Leb. I think it's still for Paraskevi and John, right?
1 second. The second.
Sorry.
Sorry. Just okay. The first one, and then I'm adding the second. So now we should have the two comments in. Okay, and anyway, they are in the YouTube chat, so they are preserved there. So thank you, John, for this.
Perfect.
Okay.
Perfect. No, and thank you, Monica, for seeing this. I mean, like that, you can see that we are actually live and that we didn't pre-record this. So I think once again that there was another question by Lev. It was, I think, for Paraskevi and John, if I understood correctly. If you had any success with MT5 transformers.
You can hear me, but I can take that. Second comment by that was copied by him because multilingual T5 didn't work perfectly well. So it was in fact the repository with a code from that repo shared by Monica, who I thank very much.
Okay, we were hearing you quite
let me can you? No.
Still very metallic, but I think we understood.
I will write in the private chat then my listening process.
There was a lot of feedback, so I will we will put it here, and in in the meantime, we can ask the audience if we have any other question. Doesn't seem to be the case, but I think that perhaps we might. I mean, we in the StreamYard live session, we might have some questions for each other, or I mean, may I abuse my position as a chairperson to ask? I was starstruck by everyone. I mean, this is really out of my comfort zone. So yeah, thank you so much for everything. But I was wondering. I mean, Isabelle, you explained quite nicely, like the struggle of every papyrologist / paleographer / sigillographer. I mean, having to deal with broken texts, with lacunae, with I mean, may I ask you just a very like workflowy question? I mean, how did you select your data sets? I mean, in a sense that, I mean, did you have to look for, let's say, quite nicely preserved papyri, or was it like, okay, this is an archive, I can kind of think that the writing might be homogeneous and so on and so forth? How do you deal with, you know, mechanical lacunae, or I mean, but in terms like of project management rather than than technology?
Yeah, so it depended on the task and the research questions. So for writer identification, I went to an archive that I already knew, I have to say, that it was digitized, but also that is the largest archive from a single village. So we have 700 texts that come from a village, so you have more chance to have several writing samples for the same individuals. And then I really wanted to have solid ground truth, so I went for the notaries, because the notaries, they write similar text, the contracts, they sign, they date, and the text is rather long for papyrus. So it's not pages of manuscripts, I'm jealous, but it's still longer than a short letter or a receipt. So that's where I was hoping to find the most solid data. For the Iliad, I went the opposite. I really wanted to have something as diverse as the papyrological material. So I really went a bit random with the easiest digitized collections, and I took everything. And now with the new project, I have a collaborator whose name is Lavinia Ferretti, and we are collecting precisely dated text. And now we're picky. Now we want complete text because we don't have to be exhaustive. We need to have good quality. So if the digitization is not good, if the text is too damaged, if the ink is too damaged, we leave it for now. Because the idea is really to build a panorama by adding solid landmarks. And then let's go start with the easy one, the solid one, and then we will go with the more difficult one later.
Thank you so much. I mean, it's an understandable approach, I think. I mean, if you want to build like a base on which, you know, to build upon, you have to be picky. I mean, as you said, that's amazing. Thank you so much. Should I broadcast 1 second the comment by John? Yeah. So in response, I think, to Leb's comment, so we can access the data from the GitHub repository, and this link will be posted and accessible on the YouTube chat. So don't be afraid and go and click on that.
I had a question if we still have a little time.
Yes, of course.
Thank you. I had a question for Maxime. Maxime, are you familiar with the work that has been done by the Kalfa team and Shahan Vidal-Goren on the Iliadoscope? Have you heard about this?
I'm very well aware of Shan works. For those who don't know, Kalfa Vision is another HTR software that can be accessed, such as a scriptorium through a server. We actually thought of using also Kalfa Vision for our projects, but there were like many problems with it. Also because firstly it's not free. It can be free if you know Chan, so you can have many perks with that. But also because you can't really share your models afterwards. So that was the main deal breaker for us, because we want people to use what we all actually do. But I know that he has some great models for ancient Greek printed or handwritten. So if you want to maybe look it up.
Yeah, so I have put it, sorry, I have the same problem as John. I'm not connected, so I cannot put it in the main chat. So I put it in the studio. So the Iliadoscope is a Geneva manuscript, which was annotated carefully. The 5 first books of the Iliad were line by line annotated by the team in Lausanne. And it was the perfect situation for HTR because there was still 19 books to go. And it's an interesting one because you have the Iliad and you have the Paratext that is written by the same hand. And what Shahan could show us already a year ago is that they only needed 30 pages to have very good results. And then they reached a plateau and they didn't need more, like the additional material was not improving so much. And I was wondering if in your case, it is the difference of hands that could explain, because in the Iliadoscope, there's only one hand. So do you think this is the case or other reasons?
So actually in our samples, we have 2 hands, but if 90% of the writing are by scribe A. So I don't know if maybe we had only that one hand by scribe A would have improved really our models. And also, 91% is pretty good for an HDR model that doesn't have been fine-tuned on under any base model. But I know that as you can begin to have like really good results starting from even 20 pages sometimes, if the layout and the transcriptions is fairly simple. Because if you add maybe like a manuscripts from the 16th century, as Paraskevi was telling us about, sometimes it's really difficult to with the ligatures, the abbreviations, and whatsoever. So I don't personally know the manuscript that John was working on, but if at least like the 5 first books were pretty easy on the transcriptions, then I'm pretty sure that he had some good results even with 30 pages. So that's great news. But for us, we started at 50 just to be sure to that we had enough data to obtain a good accuracy score. But maybe if we needed, if we want to do another experimentation in the near future, well, maybe we only have to train with 20 or 30 pages with these models or with our models, and then fine tune something up on that. So, but thank you. I will look it up, his work, that's for sure, more carefully at least.
So thank you, everyone. Something that we should definitely mention for at least my students is that we have a very big exercise this time, with many options that are taken from the 3 parts, let's say, of today's session. So feel free to browse everything and to go through all the required readings, because there's a lot to be learned today. At least I have. What else? I think that we can close our session by inviting everyone to join us next week on Monday, the 6th of May, at the same hour, because we will have another very interesting session on digital prosopography with our colleagues Ekaterini Mitsiu and James Bailey from the University of Vienna. So it's going to be fun. Join us, and yeah, otherwise, take care. Bye everyone. Thank you once again.
Bye.
Thank you. Goodbye.
Thank you.